because of the nice linearity of the rock fermions, we can make this identification of strain, of the effects of strain with a gauge field. Whereas in the case of non-relativistic fermions, there would also be additional terms of k.a, and so the identification is not as smooth or straightforward in that case. So here is where we see that the lattice symmetries then give rise to different number of independent coupling constants for the strain, such that this allows us to write down for a particular valley. For a particular valley, we can write down the effects of the vector potential, and it's given by the strain tensor and the coupling constant. So all of that was for strain generically, and now we can look at what happens in particular. What is the profile of the strain as we do get in these bilayer systems? Again, we had seen from Vidya's very nice animation how the difference in the lattice constant between these two materials gives rise to causes the buildup of strain, and this strain is then can relax through the formation of dislocations, so edge dislocations, where you should imagine a whole row of atoms that are now missing running through the system. And these rows of dislocations occur at periodic intervals, as can be seen from this TEM image, which is now seen from the top, in which there's a superlattice of dislocations. And so you can see that one of these blocks is probably on the order of 10 nanometers, so that's about 10 unit cells in this. And you can see that this is a really nice regular array of dislocations, which is pretty cool because often we think of dislocations as being a large uncontrolled strain to the system that it's going to be very difficult to predict the result of. And in this case, because it's so nicely organized instead, that it does alter the electronic properties in a way that we can model. And you can see that that these dislocations occur in both axes, in both directions along the crystal axis. So having said that, we can go ahead and model this, and we can consult classical strain theories to give us what is the strain profile from a single dislocation, and sum them up because they occur in regularly spaced distance apart, to obtain the total strain profile. And this is along one mirror axis, and then of course we have similar behavior coming from the other mirror axis. And again here we can, since we know the material parameters such as the Poisson's ratio, the lattice constant, etc., then we can actually estimate what kinds of strain we expect here. And we can put this into our equations. We have both the coupling, both the degree to which strain couples as a gauge field, and the strain field itself. And we can take the curl to then obtain a resulting magnetic field. And so, looking at the numbers that we have maximum fields in the order of a couple hundred Tesla. And again, because we have to take the curl here, we do need a spatially varying strain in order to produce a non-zero field. And so this comes out very naturally from the fact that we have this periodically varying strain profile from the dislocation. And this gives rise to this periodically alternating field that averages to zero, that features a positive field and negative field. So just to contrast this with our other favorite Dirac system, graphene, in which they also have seen pseudomagnetic fields and resulting Landau levels, as you can see from this STS spectra. Some differences here is that in here, the nanobubbles of the strain nanobubbles occur in localized regions, so individual nanobubbles. And instead, in contrast, our system, because the strain is produced by this dissipation array that actually covers, as you saw, macroscopic regions, it covers the entire sample in this very regular manner. So it can alter the electronic properties in a global fashion, and not just in a localized fashion here. And this was something that and this resulting periodic field that we get that alternates or the whole sample actually we realize that it's actually much more realistic to have a periodic field like this instead of what one might imagine as, being the first field that one thinks of would be a uniform magnetic field. But a uniform magnetic field would actually require a divergence potential, and this would imply a strain field that diverges at the boundaries of changes and magnetic field. So this is nice that our system, allows all of these nice properties. And so, having said that, we can then go ahead and look at what the resulting electronic properties of the system are. No surprise, we get Landau levels, and then we can then look at whether some of the consequences, what some of the properties of this are. So, what would we expect realistically? When the dislocation array varies on scales that are larger than the magnetic length, then we would still expect the formation of local Landau levels. And since this is true in our case, since from our estimate we do get a fairly large magnetic field, then we can still use this local Landau level approximation, in which now here we will expect for the energy level space to depend on a local field strength. So since our field is varying, we also get an energy level that's varying. And the nice thing about Dirac fermions, as Lydia pointed out also, is that the zero Landau level is always at zero energy regardless of the field strength. So that even as our energy level spacing varies, however, we still will have always extensive, we will always still have states at zero energy. This implies an extensive degeneracy of state at zero energy. And we can put this, we can then calculate this by adding a periodic field into a Dirac Hamiltonian, and then a sinusoidal field. And here we do see, as we expect, absolutely that we get a flat band in the direction of this periodicity, and in the transverse direction it is flat, close to the Dirac cone, and then there is a dispersion away from that, which you would expect since there are regions of transition between the regions of large magnetic fields. And there are two flat bands which correspond to the regions of positive and negative fields, as you can see, and you do see that the higher Landau levels are separated from the zero Landau level by a decent band gap. There was a picture in momentum space, and we can then plot the density of states in real space, and we do see that as expected, we do see a large density of states at zero energy, and further, that there are dispersive states at the transition region, which correspond to the chiral snake state of the zero Landau level. And this is the half conductance that one would expect for the zero Landau level of the Dirac fermion. And in fact, so in each transition region, one gets half a conductance coming from a region of positive field, for example. And in this one, it would be a region of negative field, so then there would be half a conductance in the other direction. So this would add up to the chiral snake state in these transition regions. So if we add the corresponding edge states from the perpendicular direction, from the transverse direction of the other mirror axis, then we do get this grid of snake state. And at the same time, like, all of this is still physics just from two of the valleys, and if we take physics from all four of the valleys, and so the time reverse physics as well from the other two valleys, that would basically be this picture, but then we add another of this, but flips over, so the time reverse physics and the jointly give physical state. Yes. So this snake state is a term that there came out in a paper of Patrick and some others about 15 years ago in which they had a different model, but in their model they had regions also a sort of positive and negative fields, and the idea is that since these are edge states, so there's this idea of curving around these individual regions.